Welcome to RO Design Library. In this video, B13, we dive deep into multimedia filter design for reverse osmosis plants. Here's what we'll cover today. Importance of pretreatment, MMF working principle, design parameters, sizing methods, economics, and best practices. Pretreatment is essential to protect expensive RO membranes from particulates, organics, and biofouling that cause rapid performance decline. RO pretreatment is the first and most important line of defense for any RO plant. Proper pretreatment removes suspended solids before they reach the membranes, and poor pretreatment selection is one of the leading causes of RO performance decline and membrane fouling. The multimedia filter is a critical first major step in RO pretreatment, effectively reducing suspended solids and preparing water for downstream processes. MMF uses multiple layers of media with decreasing particle size and increasing density for efficient depth filtration. Standard configuration: coarse anthracite on top, quartz sand in middle, and fine garnet at bottom, supported by gravel. In case of the sand filter only, 40% anthracite is replaced by 0.6 to 0.8 mm quartz sand. Common types include vertical FRP filters for lower flow rates, 1 to 200 cubic meters per hour, vertical steel filters, 200 to 1000 cubic meters per hour, and horizontal steel media filters or gravity filters, 600 cubic meters per hour onwards. Choose the design velocity carefully. Select it based on the table. However, for RO pretreatment, use a filtration velocity of 8 to 12 meters per hour to achieve good SDI reduction. Select velocity based on source water. Always validate with pilot tests for challenging waters. Basic sizing. Calculate the required filtration surface area from the flow rate and selected filtration velocity. Formulas for both vertical and horizontal media filters are provided. Let's calculate the size of a vertical multimedia filter. First, divide the filtration flow by the filtration velocity to obtain the required filtration area. Next, calculate the vessel diameter using the area formula. If the calculated diameter exceeds 3.5 meters, select two filters and repeat the calculation until the diameter falls within a practical and economical range. Calculate the required filtration area from the flow and filtration velocity. Using a 12-meter vessel length, the calculated diameter is 5 meters, which exceeds the practical transportation limit of 3 meters. Therefore, this design is not suitable for a horizontal multimedia filter. Now repeat the calculation using two horizontal filters. The diameter reduces to 2.5 meters, which is within the transportation limit and is therefore acceptable. For a gravity media filter, a single 12-meter by 5-meter filter cell is an acceptable design. For this 63-inch multimedia filter, we have selected a 1-meter media bed. The media consists of 400 mm of anthracite, 300 mm of fine sand, 150 mm of coarse sand, and 150 mm of support gravel. A 400 mm freeboard is provided for bed expansion during backwash. The vessel surface area is first calculated from the internal diameter. The volume of each media layer is then obtained by multiplying the surface area by the selected media depth. Each media volume is multiplied by its bulk density to determine the total weight required. Anthracite uses a density of 650 kilograms per cubic meter, while sand and gravel use 1650 kilograms per cubic meter. Finally, converts the media weight into the required number of bags. This provides a ready-to-use procurement list, helping engineers estimate material requirements quickly and accurately. First, calculate the filter surface area using the vessel diameter. Then multiply the area by the selected backwash water velocity of 25 meters per hour and air scour velocity of 55 meters per hour to determine the required backwash water and airflow rates. Next, select the backwash pump and air blower based on the calculated flow rates. For this 63-inch filter, a 60 cubic meter per hour pump at 2.5 bars and a 120 cubic meter per hour air blower at 0.6 bars are recommended, including a suitable design margin. To ensure performance, follow scheduled backwashes, monitor key parameters, and inspect media regularly. Monitor differential pressure. Initiate backwash when it rises 10 to 15 psi above clean condition. Mud balls form when suspended solids, organic matter, or biological growth accumulate due to inadequate backwashing. These hard deposits reduce filtration efficiency, increase pressure drop, and create uneven flow through the filter bed. To avoid mud ball formation, perform effective air and water backwashing regularly, and replace severely fouled media if necessary. Channeling occurs when water flows through preferred paths instead of the entire media bed. It is usually caused by poor media distribution, improper backwashing, or media fouling, resulting in reduced filtration efficiency. Media loss occurs when excessive backwash flow carries filter media out of the vessel. Damaged under drains, incorrect backwash velocity, or improper media grading can gradually reduce bed depth and filter performance. Insufficient backwash flow or a short backwash duration prevents proper bed expansion and cleaning. As a result, trapped solids remain in the media, leading to mud ball formation, channeling, and higher pressure drop. Multimedia filters offer higher dirt holding capacity, longer filter runs, and better effluent quality with lower turbidity and SDI. They are cost-effective for large flow applications, provide reliable operation, require less frequent backwashing, and significantly improve RO membrane performance and service life. Multimedia filters require proper backwash design and periodic media replacement, typically every 5 to 10 years. They cannot remove dissolved salts or contaminants and therefore must be combined with other pretreatment processes for optimum RO performance. The Quick MMF selection table helps engineers rapidly identify the most economical multimedia filter configuration based on the required filtration area. The table is arranged from the smallest and most economical vessel sizes at the top to larger industrial vessels at the bottom. For example, a flow of 200 cubic meters per hour at a filtration velocity of 10 meters per hour requires 20 square meters of filtration area. Use the table to select the most economical MMF configuration. The 63 inches x 67 inches 10 nose option is the most economical because it is the first configuration that meets the required 20 square meters filtration area. Larger steel vessels provide excess area and typically have a higher capital cost. Finally, estimate the total cost by multiplying the price of each multimedia filter and the valve set by the required number of filters. This provides a quick and reliable budget estimate for the complete MMF package. For detailed engineering tutorials, visit our YouTube channel. To simplify your multimedia filter design and calculations, explore our automatic MMF design software at www.rodesignlibrary.com. Thank you for watching. Please subscribe to the channel for more RO design videos and visit our website for useful engineering tools and calculators.